All right, what I want to do, though, before we jump into 12.3, there's a section in Chapter 9 that we wouldn't normally cover until the very end of the year. We kind of skip around a little bit in this book to try to make it follow a path that makes the most sense. There is a section in Chapter 9, however, that's really simple, that's handy for us to know about, and that is the special right triangles. There are two of them. There are two special right triangles, a 45-45-90, you might remember from middle school, and a 30-60-90. And I want to just review that stuff, or if you've never seen it, introduce you to it. In a 45-45-90 triangle, what our goal is to be able to do with this is to be able to relate the lengths of the legs to the hypotenuse. It's really simple to do. There's one magic number associated with this special right triangle, and that is the square root of 2. Okay, the square root of 2 is greater than 1. It's about 1.4142, something like that. So it's a decimal. And it goes on forever. It's irrational. But it's bigger than 1. So if I multiply a number by the square root of 2, I'm going to get a bigger answer, right? If I divide by the square root of 2, what's going to happen? If I divide a number by a number bigger than 1, for example, if I divide 13 by 4, is the answer greater than 13 or less than 13? Less. It's going to make smaller, isn't it? Right, so I'll divide by the square root of 2 if I want to get a smaller result. Now, in a right triangle, we always know that the hypotenuse is the longest side, for sure. The two legs in this case, this is convenient, are congruent because it's isosceles. Right? The base angles are both 45 degrees, and so we know it's isosceles. So the two legs are congruent. If I know one, I know the other. They're equal. But if I'm given the length of one of the legs, and I want to find the length of the hypotenuse, I know that the magic number that connects those is the square root of 2, and I want to multiply because the hypotenuse needs to be bigger. Right? Does that make sense? So, for example, if I'm told that the length of one of the legs is 7, and I want to find the length of the hypotenuse, what's my answer going to be? Yeah, I'm going to multiply by the square root of 2, and so I'm just going to get 7 times the square root of 2. Now, it might be that they want that as a decimal in that particular question, in which case I just put it in my calculator and hit equals. Or if you want to provide an exact answer, that's it. 7 times the square root of 2. Or in Moodle, it might be 7 times squirt 2, right? SQRT. If that's an exact answer. So that's one way we can go. If we're starting with a leg, ending with the hypotenuse, we always multiply by the square root of 2. Now, what if we do opposite? Let's say we start knowing that the hypotenuse is 9. Okay, and I want to know the lengths of the legs of this right triangle. How do I get from here to here? What's the number that connects them? Square root of 2, right? Am I going to multiply or divide? Divide, because I know that my answer needs to be smaller. The leg is a smaller length than the hypotenuse. So to get from there to there, I just divide by the square root of 2. So that's my answer. Now, if I want a decimal answer, I just divide 9 by the square root of 2 in a calculator and get the decimal answer, and I'm done. If I want this answer to be exact, though, that is an exact answer. Sometimes you'll be asked to rationalize, to simplify the answer. And remember from the beginning of the year, we'll talk more about this in Algebra 2 next year, but at the beginning of the year we visited a bit about what we do if we have a square root in the bottom. We don't really want that there. If we want to simplify it, we got to get the radical out of the denominator. What was our trick? What can I do to get rid of the square root in the bottom? Do you remember? Yeah, there.
Multiply by square root of 2 over square root of 2.
Yeah, good. Then multiply the top and the bottom by the square root of 2. Now think what that accomplishes. Maybe that seems like kind of a mysterious step, but let me remove the mystery. When we multiply by a fraction like this, where the numerator and the denominator are equal, what's the value of that fraction? 1. Yeah. 100 divided by 100, 1. A million divided by a million, 1. the square root of 2 divided by the square root of 2, 1. So I'm multiplying my original answer by 1, which means I'm not changing the value. I'm leaving the answer the same. I'm just changing the way it looks. I'm just getting the square root off of the bottom. So when I multiply fractions, I multiply straight across. Now, what is the square root of 2 times the square root of 2? 2, right? And there are a couple ways to think about that. The square root of 2 times the square root of 2 is the square root of 4. And what's the square root of 4? 2, right? So the other way to think about it, which I think is even better, the square root of 2 times the square root of 2 is the same thing as the square root of 2 squared. And what happens when we square a square root?
It cancels.
Yeah, they cancel each other out. And so I just get 2. On the top, I just get 9 times the square root of 2, and that's all I can do with that. So I get 9 radical 2 all divided by 2 for my answer, if I need to simplify it. If it doesn't ask me to simplify it, that's fine. That's an exact answer. But if it gives me specific instructions to simplify it, then I got to get that radical off the bottom. Okay? So the magic number for a 45, 45, 90 is square root of 2. No big deal. All right, what about the other special right triangle? 30, 60, 90. This one's a little more complicated. Not terrible, but a little more complicated. This time, unfortunately, we don't have any congruent sides. They're all different. So we know that we're going to have, it's a right triangle, so the side opposite the right angle is the hypotenuse, of course. And then the other two sides are the legs. Let's call them S and L for short and long in this case. Right? The short leg has to be the one opposite the 30-degree angle, and the long leg has to be the one opposite the 60-degree angle, because we know that small angles look at small sides and big angles look at big sides, right? Okay, so what complicates this one a little bit now is because we have 3 different lengths of sides, we're going to need more than one special number to describe this triangle. Now, the way we do this, if you get this from the start, this ends up being pretty simple. The way we do this is we're going to connect the short leg is always going to be our middleman. That's going to be the side that we're always going to compare to the other two. The magic numbers that relate the short leg to the hypotenuse and the short leg to the long leg are the numbers 2 and the square root of 3. I got to change something. I've got something incorrect up here. I can't believe I did this. That's not right. What's bigger, the square root of 3 or 2? 2 is. Yeah, you're right. 2 is. Because 2 is the square root of 4, isn't it? Right? Square root of 4 must be bigger than the square root of 3. So if I wanted to rank those numbers by size, we know that 2 is greater than the square root of 3. Now, just like before, if I want to start with a number and create a bigger number, I'm going to multiply by one of these special numbers, because they're both bigger than 1. If I want to get a smaller result, I'm going to divide by the special number. Okay, but wouldn't you agree that the hypotenuse is the longest side, and the long leg, even though it's longer than the short leg, is still less than the hypotenuse, right? So the magic number that must connect the short leg to the hypotenuse, because the hypotenuse is the biggest, is 2. Okay? So we always know in a 30, 60, 90 triangle that the hypotenuse is always twice as long as the short leg. That's the number that connects those two sides. The number that connects the short leg to the long leg is the square root of 3. Okay? So now, don't say anything out loud. I want you to just try this on your own here. What if I was given that the short leg had a length of 5? Okay, the short leg has a length of 5. And I want to find the other two sides of that right triangle. I want you to think to yourself what you would do. What's the hypotenuse? 10, right? Because the number that connects the short leg to the hypotenuse is 2. And the hypotenuse is bigger, so I have to multiply by that number. Right? I'm starting with the short side, getting a longer side, so I'm going to multiply by the magic number. So I get 5 times 2 is 10. Okay, what's the length of the long leg? Yeah, I'm going to multiply 5 this time by the square root of 3 to get a bigger answer, because that's a longer side, right? So 5 times the square root of 3, or 5 radical 3. Now I've got all 3, okay? So that's pretty simple. What's a little tougher is if we start with one of the legs other than the short leg. Let's say, for example, that we're going to start with the hypotenuse. Okay, what if I know that the hypotenuse has a length of 14, and I want to find the lengths of the 2 legs? Okay, you may have a suggestion about what I would do first. Yeah, divide by 2. Good. Because there is no direct connection between the hypotenuse and the long leg, is there? We always have to go through the short leg first. So 14 divided by 2 would be 7. Okay, so we got the length of the short leg, and then to get to the length of the long leg, multiply by square root of 3. So I get 7 radical 3. Okay? Make sense? See how we're doing that? Okay? Okay. All right, let's try, how about we'll quickly look at maybe one more example. Okay, try this one. Try that one. If I'm given 30, 60, 90 triangle, I'm only given the length of one side of that triangle. Fill in the other 2. Take a second. You can come up with those answers. So we got to find S and T. Okay, suggestions. How do I solve, which one do I solve for first, S or T?
S.
Got to solve for S. So what's the number that connects 5 and S? Square root of 3. Good. Okay, so I know, whoops. That's the number. If I want to solve for S, what am I doing with the square root of 3 there? Am I getting a shorter or a bigger side? Shorter. So do I multiply or dividing? Dividing. Aha. So S would equal 5 divided by square root of 3. Good. Okay, now, what if I need to rationalize that? How do I get rid of the square root of 3 on the bottom? Perfect. Square root of 3 over square root of 3. So on the bottom, I get 3 like I need. What do I get on the top? Good. Okay, perfect. So we got S. Now what? How do I get to T?
I do by 2.
Okay, I'm going to take that answer and multiply by 2. So T would equal this. If I'm multiplying a fraction by 2, how do I want to write the 2 probably?
2 over 1.
2 over 1. And when I multiply fractions, I multiply
Over.
straight across. Okay, now here's where sometimes we have difficulty. Sometimes this isn't a big deal, but sometimes there's a common mistake people make when they multiply the top out. What's the answer?
10 times 2 times 4.
10 times the square root of 3. Now, sometimes people want to do something like 10 times the square root of 6, or 10 times 2 times the square root of 3, and they end up, but we don't do that. That's double multiplying. And here's the example. If you ever get confused about this, take a simple example and ask yourself how you do this. How do I do a simple example and apply it to the more complicated example then? For example, what if I have 2 times 3 times 4? We all know what that answer is. What is it? 24, right? Everybody would have told me 24. But sometimes people, when they're doing more complicated, bigger numbers, they might try to distribute the 2 and do something like 6 times 8 is 48, which is clearly wrong. When we multiply a string of things together, we just have to multiply in pairs. Now, it doesn't matter the order in which we multiply those, though, right? Because multiplication is commutative and associative. So I could, for example, 2 times 3 is 6, times 4 is 24. Just as easily, I could say 2 times 4 is 8, times 3 is 24. Or 3 times 4 is 12, times 2 is 24, right? They all work. So when I multiply this one straight across, on the top, I've got 3 things I'm multiplying. 5 times the square root of 3 times 2. Which 2 do I clearly want to group together first?
2 and 5.
Yeah, the 2 and the 5, right? 2 times 5 is 10 times the square root of 3. Well, there's my answer. 10 radical 3. Okay, and then on the bottom, I just get 3. Make sense? If you can do that one, you can do any of them. Okay. That's it for that section. Now, there's not a ton to it. The assignment's not very long, but I wanted you to just kind of get used to how that works. Okay, so now why did we do that? We did that because we wanted to be able to jump ahead and look at, let's get out of there. Okay, because of this. Whole point was we want to be able to look at section 12.3 stuff. Surface areas of pyramids and cones. Cones aren't that big a deal. They're really not. Just like, wouldn't you agree from the 12.2 stuff, if you've either completed it or worked in it enough to kind of get a feel for it, aren't cylinders easier to work with than pyramids? Than prisms, don't you think? By the same extension here, extending the same logic, you will find that cones are easier than pyramids. Pyramids are the ones you want to really focus on. Okay, so let's start off with pyramids. What are they? What do they look like? What are their parts? Etc., etc. So this is a pyramid, like you might expect. A pyramid has a flat base that we would set on the coffee table, right? And then it's got some vertex, which is going to be above the base. The vertex is where all of the faces come together at a single point, right? So that's kind of the picture we can create. The base, we could say, has edges around it that we call base edges. And then the faces on the sides, the lateral area, these lateral faces have edges between each other called lateral edges. Okay? So there's a picture, just like the picture in your book, no big deal. Okay, that's what a pyramid looks like in general. Now we would say that the height, or the altitude, in our book they call it a height, so we'll just stick with that. The height is just the perpendicular distance. If I draw this, now watch how this works. the perpendicular distance from the vertex down to the base. Does that make sense? So if I dropped a rock from the vertex and it fell vertically, how far would it fall before it hit the base? That's the height. Okay, there's another part of this, though, that's a little weird. That part probably seems okay. The other part that's a little strange, though, is this slant height business. There are two different heights that we talk about in a pyramid. There's the normal height that we just talked about, the vertical distance between, or the perpendicular distance between the vertex and the base. And then there's the height along one of the faces. That's what we call a slant height. Think of, now, the height would be how far an ant would have to climb a rope to get from the floor, from the base up to the vertex. The slant height is how far an ant would have to walk up one of the faces to get from the bottom to the top. The path has to be a perpendicular path, though. He has to walk up the face in a line that's perpendicular to the base edge. So that's what we call a slant height. That one's a little trickier. Okay, and that comes into play, unfortunately, in the formula for the surface area. Okay, what if we want to, there's an example of a pyramid. What if we want to find the area of this pyramid? Okay, I'm going to skip ahead just a little bit, and I'm going to give you the formula. We'll see why this formula works here in just a bit. But I want to give you the formula for a pyramid. Here's what it looks like. Surface area of a pyramid equals B. Notice there's only one base this time instead of two like there were with prisms. Plus, looks pretty familiar, P, perimeter of the base, times the slant height. That's it. Okay, that's the formula for the surface area of a pyramid. Now, most of that stuff isn't that big a deal. Finding B and P usually is not that big a deal. We've been doing that already. You did those steps or are doing them right now in the 12-2 assignments. That part's the same. The part that's a little different, though, is calculating the slant height. Okay, that's where we got to sometimes envision some right triangles that are actually inside the pyramid to get that slant height. Like in this case, if we imagine the right triangle that's formed by the height and this segment at the bottom, and then the slant height, that's it right there, isn't it? Now what we're told here in this case, and this is actually these are the dimensions of that big building we just looked at, the length of one of the base edges of the square base is 300 feet. Okay? So how could I calculate the area of the base then? What's B? Capital B. How do I calculate the area of a square if I know the lengths of one of the sides?
Side times side.
Side times side, right? So it's just going to be 300 times 300. 300 squared. I wonder where that word comes from, squared. Okay, so base equals 300 times 300 equals 9, followed by 1, 2, 3, 4 zeros. 90,000 square feet. It's big. What about the perimeter of the base? How would I find that? Side plus side plus side plus side. So for a square, it would just be 4 times the side length. Agreed? Is everybody with me? Okay, so if I want to do perimeter, that's just 4 times 300 equals 1,200 feet, distance around. Okay, but it's the slant length L that's, or slant height L that's going to be a little bit tough. Now, what do we know about this? In this right triangle, we know that the height is given to us. The height of this building is 321 feet, so we can fill that in. We're trying to find L, right? Now, what's going to be the length of this bottom leg of the right triangle? What's that going to be? This might help. What if I were to look straight down from the vertex on the square base, right? That's just going to look like this. right? There's the square base, right? Now, isn't that black segment just going from here to there? How long is that? If we know that the length of one of the base edges is 300, what's that distance? 150. Isn't that just half of the distance across that square? Right? Okay, so we could write that in. 150, right? Okay, now what? When we see a situation like this, I want to kind of move this up to the next level for you guys. You're doing a good job with these things. I've been watching you do these in the lab, and people have done a good job. But I want to get a little more efficient. It's time for us to take a step forward here. What's the relationship between the lengths of those three sides in this right triangle? What do we got going here? It's a right triangle. How does that work? If I just forgot about that one and went back to just a basic right triangle, like so, and I call the lengths A and B and the hypotenuse C, well, what do we know? Pythagorean theorem, which says what?
A squared plus B squared equals C squared.
Okay, A squared plus B squared equals C squared. Right. Now, here's what I want you to be able to do. What I want you to be able to do, and you can always write that down, but you're getting to a point where you could maybe skip to the next step. If I wanted to solve for the length of the hypotenuse, what do I have to do to solve for C there, to undo the squared? The square, I should say. Square root. Right, I'd square root both sides. Agreed? And I would get C equals the square root of A squared plus B squared. Right? We know that. We know that we always have to square root the sum of the two squares to get the hypotenuse. Now, let's contrast that to, what if I were solving for B? If I were solving for B, wouldn't I have to subtract A over here and then subtract A squared and then square root? Everybody with me? So if I wanted to solve for B, I would get the square root of C squared minus A squared, right? And what if I wanted to solve for A? Then I would subtract B squared to this side and square root it. So I would get the answer A equals the square root of C squared minus B squared. Okay, that's never going to change. That's always going to be the same. So I know that if I'm trying to find the hypotenuse, it's always going to be the square root of A squared plus B squared, where A and B are the legs, the sum of the squares, right? If I'm trying to find one of the legs, it's always going to be the square root of the hypotenuse squared minus the other leg squared, right? How come I have a minus sign here and a plus sign there? Because the hypotenuse is the big side and the legs are the short sides, okay? So you can always kind of skip that step. You'll do this so much in math in your futures that it may seem like a small thing, but that little bit of extra efficiency, just being able to jump right to one of these three situations, will save you hours and hours of your life that you could spend doing other things if you can just get used to that. So if we go back up here then to this situation, what's L going to equal in terms of a square root? L is the hypotenuse, right? So L must equal, let's go down here. What's L equal to? It's the hypotenuse. So the square root, right? I always know it's a square root if I'm solving for one of the sides. Is it going to be a plus or a minus situation? Plus, because it's the hypotenuse. 321 squared plus 150 squared. Okay? And that's just going to give me a number. Okay? And when I get that number, I can plug it into my formula with the other numbers. Right? I found the base was 90,000. Perimeter was 1,200. I put that in my calculator. I get an answer and multiply that times P. Okay? No big deal. The hardest part was finding L, but it's not that big a deal. Okay? Does that make sense? Okay? Let's look at one more example. Okay, what about this one? This looks terrible. Okay. We've got a regular hexagonal pyramid because the base is a hexagon. It's regular because everything about it is that could be congruent is congruent. Right? The hexagon is regular. The vertex of the pyramid is right over the middle of the base. So all the faces are the same. They're all triangles that are congruent, all 6 of them. Okay? What if we want to find the surface area of this thing? Well, one thing that's kind of nice, I want to point something out here. Notice that I could, if I forgot the formula on the SAT test, they'll probably give it to you anyway, but what if I didn't have the formula? I could always just add up the faces one at a time and get the answer, right? If I unfold this thing, if I were to cut it along the lateral edges and unfold it, we call this a net, I could take each of those 6 triangles, they're all congruent, right? Yeah, I'm just going to wait and make sure everybody's with me. Yeah, if I found one of those triangles, I could just multiply by 6, right? And then find the area of that regular hexagon. And it might be a little bit of a challenge, but I could do it that way. It'd be fine. But let's go ahead and do this one using our formula. S equals B plus P times L, where L is the slant height. Okay, to do that, we got to get that slant height, right? So let's talk about that. How can we get the slant height? Okay, so there's our picture. We got to draw ourselves a little picture here, don't we? Okay, we got to get the slant height. Well, there's our right triangle. There's the center. The slant height has to go from the middle of this face up to the top because it has to be at a right angle. And so I've got to take that triangle out and figure out what it is. Okay, now I'm given slant height in this case. Actually, hang on, let me restate that. Jump the gun a little bit. Do I have to do a calculation to find the slant height this time? No, they gave it to me this time. So this actually ends up being an easier problem in that sense. They gave me slant height. Instead of giving me height, if they had given me height, the distance from there to there, I would have had to have figured out what slant height was, but I know it's 8. Okay, so I just got to put the pieces together then. I want to put the pieces together so I can come up with the surface area. So base plus perimeter times L. Well, I know what L is. There's L. Okay, what's the perimeter of the base going to be if the length of one of the sides of that regular hexagon is 6? How many sides in a hexagon?
6.
6. So what's it going to be? The perimeter, distance around. Yeah, 36, right? I've got 6 sides times 6 meters per side. Right? So we know that the perimeter is 6 times 6 equals 36. Okay, good. What about the base area? That's a little trickier. I got to find the area of a regular hexagon. Okay, we can do that, but it is a little trickier. So there's the hexagon, right? I know it's 6 meters on a side. Okay, how am I going to get this? Well, they threw something in there that we don't necessarily know right away. If it's 6 meters on a side, there's a couple ways you can do this. Now, what if I cut this whole hexagon up into triangles? I want to show you something tricky here. So we went from there to there, from there to there, there to there. Okay? What can you tell me about those triangles? Each of those 6 triangles. Is there anything special about it? What do you think, John? They're all congruent. That's true. What else? Anything else? Equilateral. How come? You're right. How come? They kind of look that way, but how could we show that they have to be? Okay, that's 6. What do you think?
If it's a regular hexagon, that's
Okay, it's a regular hexagon. Now, here's one way we could do it. Now, watch closely here. how many degrees are there if I were to travel all the way around this thing from here? Whoops. If I were to travel all the way around this thing from there to there, how many degrees is that? 360, sure. Now these are all, it's a regular hexagon. All these triangles are congruent. You already told me that. Well, if that's 360 degrees all the way around, notice that there are 1, 2, 3, 4, 5, 6 triangles in there. What's going to be the angle of each of those individual angles for each triangle? Yeah, 360 divided by 6 is 60. How about that? So if that's 60, let's take one of these triangles. They're all the same. So let's take this top one. If that's 60 degrees, well, I know that it's that the triangle, that these two angles have to be the same, don't they? Because it's regular. Agreed? So there's 180 degrees total. If that's 60, the other two must add up to 120, and they have to be congruent. So what are they?
60.
Yeah, they're 60. So if it's an equiangular triangle, then it's also equilateral. Aha, that's good. So if it's equilateral, then we know that we have a formula for that. We know that the area of an equilateral triangle, you remember, I need to make a formula sheet up for this chapter. I haven't done that yet, but hopefully you're doing it in your notes. What was our formula for calculating the area of an equilateral triangle? Instead of having to use half the base times the height, what were we able to do instead? Remember how we did that? We could multiply, it was the fraction, the square root of 3 over 4 times s squared. Remember that? Okay. So one thing we could do here is we could just find the area of one of these triangles by multiplying the square root of 3 over 4 times 6 squared, and then just multiply that by 6. That would work, wouldn't it? Okay. If we want to use the formula, does that make sense? Is everybody okay with that? Let's do that. Let's just make sure everybody is okay with that. So if I plug in the numbers, I get the area is the square root of 3 over 4 times 36. 36 over 1. Can I reduce that at all? Yeah, 36 over 4 reduces to 9 over 1. So I would just get 9 times the square root of 3. So that's the area of that triangle multiplied by 6. So the total area of the base then is just 6 times that. 6 times 9 is 54. So 54 root 3. Okay, does that make sense? That works. That's fine. The other way, we're not going to have time for it. Okay, this is really the last one I want to finish up, and then you're good to go for quite a while. All right?